Welcome back to the Red Car Analytics Learning Path. My name is Neil Bolger again, and this is the second video in Modeling with a Purpose, where we are talking about making energy models and why we do that, and then how we do that, kind of some of the overarching things about what is an energy model, and is really what we're going to dive into in this video for people that are just getting started and may not be as familiar. So in the last video, we talked about the value, some of the ideas of balancing deliverables with the software you might be using. But I wanted to take a further step back and just talk about, what is it that we're actually doing? And in a lot of these things with a building energy model, what we're trying to do is really represent the energy flows between the environment and a building. So some characteristics, there's lots more, but that might encompass the environment for your site, the seasons, the weather, latitude, longitude, how much rain falls, and then the energy flow to basically move heat, move fresh air between a building. The heat might actually be inside the building. We have space uses, people bring computers into buildings and turn on lights, and that heat has to get out of the building and sent to the environment in order for the building to not overheat. So a lot of times, our model is just a representative structure of this energy flow. Most energy models now are run annually, every hour, if not more granularly. But there are ways to do this same analysis with other shortcuts using bin analysis or just thinking about a certain period of time. But we're mostly going to be talking about annual energy modeling. So I like to think about starting from the top, all the different things I need to do to build my energy model, even if it's a simple model in the beginning of a design, or if it's in the detailed phase of a design, or if it's already built and I know a lot about the systems. I still take the same approach. So, define weather information, picking a weather station. So you might be here where you have a site that's near a weather station that you can use, and that's a great way to then say like this is close enough, or maybe it's not, and you want to actually buy weather data that's closer to your site. But there's lots of different ways to find weather data. And you can see here there's different representative weather data comes in two types. It comes in a file that will give you an hourly representation of every day, every hour of the year, and that's called a weather file. We also need a design day. A design day represents either the hottest or coldest conditions that location experiences. And these design days are used to help understand how big should the heating system be or the air conditioning system be. And if I was to estimate that size, if I didn't put it in myself, I need to reference a condition, a design day condition, such that I know I can heat my building in Santa Barbara here to 34.7 degrees outside. I can still meet 70 degrees inside. So how big is that heater? There's a whole world of design day information you could dive into, and the art of mechanical engineering and sizing. But for energy modeling, just know these are two different things, both related to the weather and a certain location. And they usually come together. You'll find them if you download weather data. It comes in a zip file with a DDY file, design day, and an EPW, which is an annual weather file. You can see here, this is an old map. There's different tools now online, but this one just represents where there was weather files available at the time. There are lots of ways to find weather files. You can find them now for actual years. You can actually even use other software that will interpolate between them if you are here, and it will try and give you a weather file. Sometimes those aren't the best, but they do exist, so there's more and more resources for people. This is just a way of looking at weather data on a psychometric chart. I'm not going to go through this now, but there's lots of great things. Orientation, more important than you could think. So is your building actually facing the right direction? Is it facing north, south, or east? Do you have a reference point? Making sure you set this is important. It's very important. It can change all the answers if you just leave it to be the default. So if we define the location, the next step is really to say, how is the building used? What are the space uses? And more, there's actual information available from real uses in different spaces. People are even doing plug load studies But there are references. So there's energy standards, both in California as well as across the United States. Here, ASHRAE 90.1 is a standard created by ASHRAE that is used throughout the United States. Both of these give a list, a starting list of common representative, they call them non-residential space types. So offices, conference rooms, corridors, and they give information about, well, how many people are usually in those spaces? What square feet per person would you expect? What's the lighting amount you would install? What power in watts per square feet of floor would that space have? And it includes everything from these density numbers to schedules that represent those spaces for usage. So you represent throughout the day. And so to give an example, here's that table. Again, this is an old one from Title 24, but we can see here receptacle loads, different space types, beauty salons, 2 watts a square foot, lots of other inputs. Even domestic hot water is in Title 24, so you can figure out the amount of hot water per person in a building. To give you a sense of schedules, I talked about this a second ago, but with each one of those space types, there'll often be lots of different schedules that represent perhaps equipment in the buildings. So you can see here the equipment coming on, and they're usually fractional, 0 to 100%. And we can see then on the weekends, the equipment is off, not as many people. And here you actually see a different equipment schedule. This one represents actual people and their body heat coming in. So these are all also inside these reference manuals. So space types, and we'll look at space types and we'll assign them. And there's lots of ways to quickly add space types now in templates, and you don't have to actually dive in all the details, but you still want to make sure you get them right and you're a close match with what the building's use actually is. Similar on constructions, you can go super deep into constructions and envelopes and assemblies. Again, though, there are references of pre-built walls, windows, glass types. It definitely is worthwhile to become very educated in what it means to build up a wall from different materials and what type of insulation you can expect. But as a starting place, there are lots and lots of template construction types. And again, these standards will help you. This is a representation again from California. It's a lot of numbers in a table, but what is we're able to glean from this is that for each climate zone, which is a different column in California, there's a different minimum insulation requirement for all these different pieces. So a roof has to be at least this insulated, and a wall of this type has to be at least this insulated. And glass installed prescriptively in this climate must have this solar heat gain as a maximum. So there's different max and mins. They're all in the code, but the nice thing is a lot of these construction assemblies are already in libraries for you to quickly pull in the construction set for climate zone 2, and it gives a good starting spot. So that's walls, right? So now we have our location, people in the building, how much thermal internal loads they're going to have. We've added some envelopes. Now we need to define thermostats and a range of comfort. So comfort is a huge topic in and of itself. In an energy model, we really need to represent how is the air temperature being controlled, and in some buildings, how is the radiant surface temperature being controlled. You could think of this as if there was a floor that actually had cold water running through it in tubes, it might be changing the surface temperature, and that can contribute to comfort. There's lots of different tools to help understand a range of comfort. This is a tool from the Center for the Built Environment. I'm not going to go over in detail, but what we're seeing here is this is the design point that we've entered, and this is the range where people would be comfortable. We can see from this standard, this ASHRAE standard on comfort, standard 55. There's different ways to think about comfort inside buildings, in naturally ventilated buildings. A lot of the metrics are actually merging together. Comfort is a deep, deep topic. Personal comfort is an even deeper topic. But basically, we need to define how is comfort in our building being represented. Once we do that, we can then start to think about how are we actually heating and cooling this building. Is it a passive building? Is there no active system? Or is there an active HVAC, heating, ventilation, and air conditioning system? and what does that system look like? There's lots of references. Here's one that gives guidance on passive systems. It's a huge book, spreadsheet, PDF. There's lots and lots of resources in this guide on how to think about passive systems and what those look like. And they can even be used in an energy analysis. This is a great basis to get started. Think of this as the back of the envelope tool. And then again, ASHRAE 90.1 and other standards provide a reference for what a basic system looks like and what minimum efficiency looks like in different locations based on climate and then size of building as well. And we'll talk about systems in the end. So really, that's the workflow. You're going to work on building it up, putting in basic information envelope, comfort, and then building out a system. Quality control is a challenge, right? There's going to be lots and lots of inputs, and we're also doing lots and lots of things by assuming that these templates are representative of our building. Are those plug loads in that template of that space type the most accurate for your client's office? Maybe not. And so thinking about how these inputs change the output is kind of the key to making a robust model. And at the same time, there's lots of ways you can do quality control. I would almost say visualization is a way of even doing quality control, like having enough visualizations of the data coming out and the inputs can be a way to check your model. Simple hand calcs as well, great way to kind of check. There's ways to almost say, in my climate, I know how many heating degree days there are, and then you can use that plus the envelope to try and estimate how much heating energy you should have with a certain insulated envelope. So there's ways to kind of say, like, is my number 300% what it should be? Like, that's the real goal of like self-quality control, is to get numbers to be more 10 to 20% of where we think they should be. So with that, that's my basic intro again to energy modeling. We're actually going to jump back. Thank you for modeling with a purpose, and I will talk to you in the next video.